Hello everyone. So in this video, we are going to look at some of the previous year problems from the aerodynamics section of GATE 2008, GATE Aerospace 2008. So we'll be looking at those problems and then trying to understand the concept behind them, and then we'll be trying to solve it. And for in fact, all the aerodynamics problems from that GATE paper. So let's go to the first problem in which they're asking us the maximum thickness to chord ratio for NACA 24012 airfoil is. So NACA 24012, so it's a 5-digit airfoil. 24012. It's a 5-digit, 5 series is basically what they would call it. 5 series airfoil. 5 series. So basically what that means is, they'll have some designated values that each of these numbers signify. So for a NACA 5 series airfoil, the last 2 digits, that in this case, which is 12, when I gives you the maximum thickness to chord ratio in percentage. So what that means is that 12 by 100, that is the last 2 digits, times the chord, it basically gives me my maximum thickness to the T max to the chord is basically what it gives you. So so in this case, the maximum thickness to the chord ratio for NACA 02401 to airfoil is nothing but 0.12. So this is nothing but T max, not T max by C, but just T max. So that is the significance of the last 2 digits, and that is basically the answer to this question. That is option B. So just to repeat it again, the last 2 digits multiplied by the chord divided by 100 basically gives you the maximum thickness. So the maximum thickness to the chord ratio becomes 12 by 100 in this particular case. And just to talk a bit more in detail about what the other digits mean. So the first digit, that is 2 in this case. So if I take the first digit and then multiply this by 0.15, I get what is the design CL. CL design. So design CL is basically nothing but the optimal value of CL over which this airfoil can be used, or it basically gives you the CL value for which this airfoil was designed and gives the best performance. And then the next, the second and the third term mean here is that is nothing but 40. So if I do 40 by 2, that is the second and the third term divided by 2, I get 20. And the significance of this number is that this basically tells you in percentage of chord where the location of my maximum camber is. So what I mean by that is if I do 20 by 100 times the chord, it gives me the location of max camber. All right. So that is basically from the leading edge, if I go to a location of 0.2 times C, I get the location of maximum camber. And then the last 2 digits basically gives you the maximum thickness to the chord ratio, that is 12 by 100 times C. And then the design CL value is given by this number that I mentioned, that is first digit times 0.15. All right. The next question they're asking you, the maximum possible value of pressure coefficient in incompressible flow. So Cp for an incompressible flow is defined as P minus P infinity divided by half rho infinity V infinity square, where infinity refers to the free stream quantities like pressure of the free stream, density, and velocity of the free stream. And P is any point in the flow field where I want to find my Cp. So let's say if we have a flow over a cylinder, this P could be any point that I'm choosing on my flow field where I want to find my Cp value. And usually we find the Cp value over the surface of a solid body, because that is what basically gives you the net force acting on that body, right? And for an incompressible flow alone, applying Bernoulli's equation between the free stream and the point that you want to find the Cp, I can narrow this guy down to expression 1 minus V by V infinity whole square, which you guys would have seen in flow over a cylinder when doing that. enough for that particular case to derive the CP value. Now they're asking us what is the maximum possible value of CP, and in the question they're asking us maximum possible value. So they are not asking us whether in terms of positive or the negative sense. So in an absolute sense is what they're asking. So you can, so from this expression, you guys can see that the CP value is basically defined by the second term, that is V plus V infinity, V by V infinity for that matter. So so we have to look at how that V by V infinity will change. So CP is equal to 1 minus V by V infinity whole square, right? Now, if my V by V infinity is greater than 1, or V by V infinity square is greater than 1 for that matter. So that implies my CP is going to be less than, so that is nothing but your CP will be 1 minus some value greater than 1. So your CP will definitely be negative. So um, so let's so this is so this anything less than 0, it's definitely negative, and it's going to be, so irrespective of what the magnitude is. So this guy could be so large that my CP might be very large negative number, let's say -8, -10, etc., but still they are negative numbers, right? And so so that basically gives you a condition that, okay, if my V by infinity is greater than 1, then my CP is less than 0. So that may not be the location of my maximum CP because these are negative numbers. Now let's look at V by V infinity whole square that is less than 1. So in this case, if it is less than 1, it basically tells you that my CP will also be, so 1 minus some number less than 1 is going to be less than 1. So and let's say if my V by V infinity is equal to whole square is equal to 0, so that implies my CP is equal to 1, right? So these are three different conditions that I'm putting forth. So in the first case, its value is negative. So irrespective of how high the magnitude is, but still a negative number, so it's still lower than 1. So I'm just going to ignore this guy. And in this case, my CP is less than 1. So so while V by V infinity equal to 0, we get a value of CP equal to 1, which is definitely higher than this condition, right? So I'm going to ignore this guy. So that leaves with only the last guy, which is my CP value equal to 1. So so since in this question they have not asked us whether to look at the magnitude alone or magnitude and the sign, so I'm going to consider both magnitude and sign together. So going by that argument, when my V equals to 0, that is where I get my CP to be 1, and that is basically my highest value of CP that can be observed in the domain. While the other conditions where CP is less than 1 and greater than 0 or greater than 1, all gives you values much lesser than 1, both when considering both sign and magnitude. So the right answer to this question would be option B. Right. Now, in this question, a theory question, laminar flow airfoils are used to reduce. So laminar flow airfoils are nothing but some kind of particular type of airfoils which gives you the best performance as long as the flow is laminar, or they ensure that there is a laminar flow over the airfoil, providing very little turbulence to the flow field. So we use such airfoils. The main reason why I use laminar airfoil is to prevent the flow becoming turbulent. So and all of us know that when the flow becomes turbulent, we see that your skin friction increases, right? Skin friction increases. Skin friction increases, while your pressure drag will decrease. While in a laminar case, your skin friction is, let me call skin friction as SF, is lower, while your pressure drag might be higher, right? Because of the flow separation. And in turbulent flow, because of the eddies being formed, your skin friction is definitely higher, but because of turbulent flows are less susceptible to flow separation, your pressure drag is going to be lower. So when using laminar airfoils, we want to make sure that your skin friction is as low as possible. So that is why when using laminar flow airfoils, the main idea behind is to reduce the skin friction as low as possible. While the trim drag, not related to using laminar flow airfoils, the induced drag is for a finite wing, not for a particular airfoil. So we can ignore that. And wave drag is especially when you have very high speed flows, and in high speed flows definitely you can't make sure you can retain your laminarity condition in more cases, in many of the cases. So the right answer would be skin friction drag. So laminar flow, because compared to turbulent flow, your laminar flow will give you better performance in terms of skin friction. All right, now let's look at this simple problem. Consider a symmetric airfoil at an angle of attack 4 degrees. So you have a symmetric airfoil, and so which a symmetric airfoil, which basically tells you that alpha L equal to 0, lift angle of attack is nothing but 0 degrees or radians, and it is flying at an angle of attack of alpha equal to 4 degrees. Using thin airfoil theory, the magnitude of moment coefficient about the leading edges. So you have to use thin airfoil theory and find what is the moment coefficient about the leading edge. This is the leading edge. All right. So from thin airfoil theory, we definitely know that the lift curve slope, that is dou CL by dou alpha, is nothing but 2 pi per radian. Per radian, right? So this is something which we already know beforehand. And they're asking us to find the moment across the leading edge. So there are two ways to do this. One, is a very straightforward. From thin airfoil theory, we know that the moment across the leading edge is basically given by minus CL by 4. So minus CL by 4 basically gives you what is the value of moment coefficient of the leading edge. So direct simple formulas from the thin airfoil theory. So let's use this first. So CL in this case will be nothing but dou CL by dou alpha times alpha, and we do not have alpha L equal to 0 is basically 0, right, for a symmetric airfoil, and that is CL value divided by 4. So dou CL by dou alpha is nothing but minus 2 pi divided by 4, and alpha is 4 degrees, which we need to convert to radians. So that is nothing but 4 into pi by 180. All right. So I'm going to multiply 4 into pi by 180. All right. So 4 I can cancel out, 2 and 180 becomes 90, and pi square. So my CM across the leading edge is basically nothing but pi square by 90, and negative sign indicating that it's in the anti-clockwise direction. All right, so basically nothing but option D. But there is another way to do this as well, more from like fundamental principles. That is, let's say you take your symmetric airfoil using engineering mechanics, basically. So we know that for a symmetric airfoil, let's say I have my quarter chord point, right, which is nothing but the aerodynamic center. And the quarter chord point, let's say my CL is acting in the quarter chord point, and the moment across my quarter chord point is 0 because it's the aerodynamic, and it's also an aerodynamic center, basically. So I know that moment across my quarter chord is 0 for a thin symmetric airfoil. For thin symmetric airfoils. All right. Now with this idea, I'm going to transfer all these moments to my leading edge. So moment across the leading edge would be nothing but a moment at my quarter chord. And then when I'm transferring my CL value over here, it introduces a moment again in the anti-clockwise direction. That's nothing but CL by into 1 by 4, since we are dealing with non-dimensional quantities. And moment across my quarter chord is 0 and CL by 4. So this is basically nothing but a simple straightforward equation that we saw and solved it in the previous page, right? So again, you could always use a simple force balance and then solve it, or you could just use a straightforward formula to solve this problem, and then your right answer would be pi square by 90. So in this question, what they are basically asking us is, if the flow Mach number in a turbulent boundary layer over a flat plate is increased, a flow Mach number in a turbulent boundary layer over a flat plate is increased, keeping the Reynolds number unchanged, the skin friction coefficient CF increases, decreases, remains constant, initially decreases, followed by rapid increase. So let's look at this question. So you have a flat plate and you have free stream coming in, and with some velocity v infinity and some Mach number m infinity, and let's say the Reynolds number given by Re. What they're saying is that I keep increasing my m infinity. So m infinity is kept increasing while my Reynolds number is kept constant. So now what they're asking us is, what would happen to my skin friction coefficient? It's a very simple problem. So skin friction coefficient at every location or per unit length, I'm sorry, not per unit length, the skin friction coefficient at every location x from the leading edge of your flat plate is given by the expression which is nearly equal to 0.059 divided by Rex power 1 by 5. So basically telling you that as my skin friction coefficient is basically a strong function of my Reynolds number. So basically is a function of my Reynolds number of the free stream or what the flow. And this is the skin friction coefficient at every location. If let's say I take an average skin friction value, again, that will still be a function of my Reynolds number based upon the length of my flat plate, right? So if I were to integrate, let's say if we have the flat plate of length 0 to L and integrate the skin friction coefficient at every location over the entire length, I'm going to still get it in as a function of a Reynolds number based upon the length of the flat plate. So from this expression, you can see that, and this is for a turbulent flow to keep in mind. And from this equation, you can understand that the CF is basically purely a function of Reynolds number. So as long as the Reynolds number does not change, your CF doesn't change. So even if you increase the Mach number and keep the Reynolds number unchanged, your CF is basically going to be constant. So the right answer to this question is option C. Remains constant, because CF, which is a function of the Reynolds number based upon the location from the flat plate, and then I take the average value of the CF based upon averaging it over the entire length of the flat plate, is definitely still going to be a function of Reynolds number, right? And Reynolds number is unchanged, so CF should remain unchanged. Right. In this question, again, a very simple one. The variation of downwash along the span of an untwisted wing of elliptical platform. So you have an elliptical platform wing, and from lifting line theory, we know that when we take the special case of an elliptical wing, we have seen that the downwash is basically given by the expression gamma by 2b and gamma naught by 2b. Basically telling you that so the downwash at every point on let's say at every location on my span of the wing, my downwash takes a value of gamma naught, which is a constant, basically gamma naught. So in elliptical distribution, your gamma is given by gamma naught into root of 1 minus y square by b by 2 whole square, etc. So gamma naught is basically what is the gamma value at the middle or the center of your wing, and b is nothing but the span of your wing. Now, for the elliptical platform, we saw that the gamma distribution will also be elliptical in nature. And for elliptical gamma distribution, the downwash is given by minus gamma naught by 2b, where gamma naught is definitely a constant, right? Based upon how the distribution, based upon what is this gamma naught, the constant value or value at the center, it's again a constant, does not vary with location. And b is again a constant at the span of the wing. So basically telling you is that gamma is basically not a function of y or the location along the span of your wing. So basically telling you that downwash is constant at every span-wise location on your wing. So it's definitely going to be option D, constant. Very simple problem. In this question, flow past an airfoil is to be modeled using vortex sheet. The strength of vortex sheet at the trailing edge is. So this is something very similar to what we have seen in thin airfoil theory, where they replace the airfoil. So let's say you have an airfoil, you replace the airfoil with a vortex sheet on top and bottom, and then we assume the airfoil to be thin so that we can replace the camber line with a vortex sheet and do all our analysis based upon the camber line. And from this, we also saw that at the trailing edge is basically we saw that based upon Kutta condition, the trailing edge must either be a stagnation point or the flow must be smooth, right? The trailing edge must either be a stagnation point or must have a have smooth flow, meaning that the velocity coming from the top and the bottom must be equal. So to draw it, so if this is the trailing edge, so either it should be in this way that velocity from the top is v1 and this is v2, so v1 should be equal to v2, or if the velocity is in this particular manner, so let's say if I draw a different kind of if this is like a cusped trailing edge, so you would have velocity coming from this way and this way, and you would have v1 should be equal to v2 should be equal to 0. And in this case, it need not be equal to 0, but they should be just equal in magnitude and direction. And this is from the Kutta condition. And from the Kutta condition, we also know that the strength of the vortex sheet, not from the Kutta condition, we already know that the strength of the vortex at any given location, gamma, is given by the difference in velocity between the top and the bottom. That is, if you have a vortex sheet, the strength of the vortex sheet at a particular location is given by, let's say v1 is the velocity at the top and v2 is the velocity at the bottom. So if I take v1 minus v2, that is basically going to give me the strength of the vortex sheet at this particular location. Let me call it as x. So at the trailing edge, so now our focus is to, from the question, the strength of the vortex sheet at the trailing edge. So at the trailing edge, so if I take gamma at the trailing edge is v1 minus v2, as we know. And so as from the Kutta condition, we know that either v1 must be equal to v2 or v1 and v2 should both go to 0. So in either case, my strength of gamma at the leading edge will be equal to 0. So essentially meaning that the strength of the vortex of the trailing edge should be 0. So option A. All right. And this question, what they're asking is the geometrical features of a supercritical airfoil is. So supercritical airfoils are nothing but a type of airfoil which we use to make sure that our wave drag is as late as possible. So what I mean by that is, as we know that, let's say you have an airfoil that is flying at some Mach number, let's say m infinity. Now, as m infinity keeps increasing towards 1, so there is some subsonic Mach number, let's say for example, let's take 0.8. And at this Mach number 0.8, you could see first, and we know that the flow will definitely accelerate on top of the airfoil, and there will be local velocity, local regions where my velocity becomes equal to sonic velocity, that is equal to 1. So we know that even if the free stream is subsonic, there could be sonic velocities on top of my airfoil because of the flow acceleration. Now the idea of using a supercritical airfoil is that we want to, and this local acceleration can create shock waves and it can create huge amount of wave drag. And so that is why we want to delay this wave drag or delay such flow accelerations as much as possible. So we do not want to get huge wave drag even though we are flying at subsonic velocities. So that is why they use supercritical airfoils. So let's say if you're using a normal airfoil, you can see that the free stream might be subsonic, while the flow will accelerate and then create a huge, very strong shock wave over here. And creation of huge strong wave means that there's a huge pressure gradient, and you get a huge amount of what we call as the wave drag because of this loss that is happening. Now, in a supercritical airfoil, when I use it for the same Mach number, what it basically does is that it does not allow rapid acceleration on my such huge acceleration on top of my airfoil. And you can see that even if there's some acceleration, the shock wave created by it will be very weak and does not contribute to too much. Wave drag is still much lesser. So to create such geometric features, one thing which we definitely need is, to prevent very less acceleration happening on top of my airfoil, right? So for that, we use almost a flat upper surface. So the geometric features of a supercritical airfoil are nothing but round leading edge, flat upper surface, and high camber at the rear. So this is basically option A. So the reason why we use a flat upper surface is nothing but we want very less acceleration to happen on top of my airfoil. So we use a almost flat upper surface. And we have a round leading edge. So the reason why we use a round leading edge, because we know that the moment you have very sharp turns in the flow, right? Let's say you take a diamond shape, there is the flow direction changes so rapidly that it can create huge amount of losses, right? So we want to reduce those losses as much as possible. So we have a very round leading edge, making sure that the flow is turning in very smoothly. It does not turn in as rapidly like you see in sharp corners. So we reduce that much of losses. And high camber at the rear, so you can see that there is a high camber at the rear that is happening at the bottom surface. So that is just to make sure that even at the bottom surface there isn't much acceleration happening, and we still maintain very low Mach numbers on the surface of the airfoil. So the geometric features are round leading edge, flat upper surface, and high camber at the rear. All right, let's look at this numerical problem. Consider an untwisted wing of elliptical planform in an inviscid incompressible rotational flow. So you have an elliptical planform wing and it is untwisted. So the geometric angle of attack every location is basically the same. So the geometric angle of attack at every location, let's say if I call it alpha, is going to be constant throughout. And the elliptical planform. So elliptical planform means you'll have an elliptical gamma distribution as well. Is going to be elliptical. And from lifting line theory, we know that when we apply the lifting line theory to a special elliptical lift distribution, we know how to deal with it. And it's an incompressible inviscid rotational flow field at an angle of attack of 4 degrees. So it's kept at an angle of attack of 4 degrees. And this 4 degrees is going to be constant throughout the span since we do not have any twist. The wing aspect ratio is 7. So aspect ratio of the wing is 7. And the zero lift angle of attack is, so it's not a symmetric airfoil. So it has some zero lift angle of attack. And that is around -2 degrees. All right. Now what they're asking is what is the lift coefficient of the wing. So the first step in calculating the lift coefficient would be nothing but finding. So for a airfoil, we can assume that the lift curve slope, that is CL alpha, can be considered as 2 pi per radian, since they have not mentioned anything in that problem. And we know that when going from airfoil to wing, so let me take the small L. So when going from airfoil to, so this is for an airfoil. And if I'm going to a wing, I know that my lift curve slope is definitely going to reduce because of the 3D wing effect or the downwash effect. And that is basically given by CL alpha divided by 1 plus CL alpha divided by pi aspect ratio. And this is for an elliptical wing, right? So our Ostwald efficiency factor E is basically equal to 1. So for an elliptical wing, to find the lift curve slope for the wing coming from the airfoil, you just need to use CL alpha for the airfoil divided by 1 plus CL alpha for the airfoil by pi AR. So doing that, CL alpha is nothing but 2 pi divided by 1 plus CL alpha is again 2 pi divided by pi times aspect ratio is 7. So I can cancel out these guys, and my CL alpha would turn out to be, so this guy would be nothing but around 4.88 per radian, and definitely which is much lower than 2 pi, right? Now with that value, let's calculate what is the CL value of the wing. It's nothing but CL alpha times alpha minus alpha L equal to 0. So CL alpha, that is nothing but 4.88 into alpha is 4 degrees and minus of -2, so +2. And you would need to convert the degree to radian, so I'm going to multiply it by pi by 180. All right. So 4.88 into 6 into pi by 180. So this can be divided by 30. So your CL value over here would ultimately become nothing but 0.51. So, and that is nothing but option B. And the next question, the induced drag coefficient of the wing. So induced drag coefficient, as you guys know, can be calculated from the CL value as nothing but CDI by CDI is equal to CL square by pi AR, and Oswald efficiency factor E is 1. So CL is nothing but 0.51 square of it divided by pi times the aspect ratio 7. So CD induced, so that is basically will give you a value of 0.0118. So that's nothing but option C. So using just the elliptical distribution special case of lifting line theory formulas, we have in fact solve both these problems, and it's extremely easy. It might look like a problem which might be difficult to solve, but it's extremely easy once you understand what they're asking. Yeah. Now let's look at this problem in which which one of the following high lift devices results in higher stalling angle? So the reason why we use high lift devices is to augment the lift. So let's say you have a wing which is flying at some angle of attack alpha, let's say 4 degrees. Now it will give you some value of CL, let's say 0.1. Now the idea using high lift devices like flaps and slats is nothing but to, at the same angle of attack, I want same angle of attack of the wing, I want a higher value of CL. That is the main idea of using a flap. So let's say you have look at, let's say you have a plain airfoil or a plain wing, and then you can see an airfoil with a flap over here. So flap is basically nothing but an augmentation. Either you do it to the leading edge or the trailing edge. So you can see that this trailing edge is basically it is not just a fixed section like this. It can be moved, up and down, and by that way, you can change your you can and by that way you can just move these trailing edge location. And the effect of using a flap is nothing but, so let's say if your actual lift curve slope of your airfoil is given by the red curve. Now when you use a flap, the lift curve slope gets shifted towards the top. So meaning that for a given angle of attack, let's say 4 degrees, the red curves gives me a value of CL here, but the blue curves gives me a higher value of CL, just by adding a small a movable trailing edge. And that is how a flap works. And the main mechanism by which a flap is giving you additional lift is nothing but flap basically alters the camber of your airfoil. So let's say you have a camber line for an airfoil. Now, when using a flap, your camber becomes a bit distorted and you have a higher camber. And if you have a higher camber, you'll have more flow acceleration, and then you tend to get higher lift or CL from it. So that is the main manner in which a typical flap work, a plain flap for that matter, works. And And there are also some flaps which also does something what a slat does. So a slat is nothing but like an attachment on the leading edge of your airfoil. So this attachment can be pulled away as well as towards your airfoil. So this is an attachment that can, let's say, initially, let's say my slat is somewhat like this, somewhat here, and then joined to my airfoil with some rod. I can always pull this guy front and back, and I could always have a configuration something like this. I pulled it so much to the front that it's something like this. I'm just exaggerating, but this is how the slats work. So the main way in which slat works is nothing but as you're pulling this guy away from your airfoil, there is some amount of air from the bottom. So there's already some air going towards the top of your airfoil, and now you have some additional air that is coming from the bottom and then going towards the top of your airfoil. So this air that is going from the bottom to the top basically re-energizes the air at the top. It gives more energy, and more energy means that you'll have a much later flow separation. And if it is separating later, it'll have the stalling will be delayed. That is, alpha stall will be higher. So that is what you can see in this dotted red curve, that if I use a slat, I'm adding more energy to the flow and I'm pushing my flow separation, and I have a higher stalling angle. So flaps typically work by altering the camber line, while slats work by adding energy to the flow on the top. And in this question, if you look at, they're asking you different kinds of options, like, okay, which one results in higher stalling angle? So a plain flap definitely does not do that, because plain flap will just will give the same angle of attack, but it's just altering your camber line. And then you have a split flap. So split flap is something which looks something like this. So there's a plain flap over here. So this is a basic section, and there's a plain flap which can alter your camber line. And then there's a split flap, which is basically used as an augmentation at the bottom. So you'll always have your airfoil section over here, and then you'll have a plain flap, which will basically create certain vortices over here and help you with the flow and help you with providing higher lift. And then you have slotted flaps, wherein it not only changes the camber line, it also allows curve flow from the bottom to go to the top, just very much like a slat. What slat does at the leading edge, it does at the trailing edge. And we know that the moment you re-energize, you are going to get higher stall angle, right, from the graph we saw. So that is one way in which the slotted flap works. And then we have the Fowler flap. So Fowler flap is again very similar to slotted flap. Here, you add an augmentation at the bottom, and then at the same time, you give some allowances for the flow from the bottom to reach the top, meaning you're energizing the flow at the top, and meaning that you're increasing the stall angle and delaying flow separation. And then you have a combination of slotted and Fowler flap. So with this, so out of all these, your plain flap does not re-energize the flow. Your split flap does not re-energize the flow, while the slotted, Fowler, and all these three guys will re-energize the flow. And the moment you re-energize the flow, your stall angle is going to be higher. So out of all the options given over here, split flap doesn't do that, plain flap doesn't do that, and leading edge flap is very much similar to plain flap, but which is kept at that leading edge and changing the overall camber of your airfoil. So the right answer here is a Fowler flap, though in the answer key it's given option A, but the right answer here is Fowler flap. So basically because it's able to re-energize the flow and not just change the camber line. So here in this question, let's see what they're asking us. Consider a 2D flow with stream function half ln of x square plus y square. The absolute value of circulation around a unit circle centered at x0, y0. So you have a flow field which is given by psi is equal to half ln of root x square plus y square. All right. And now they're asking us, you have a flow field created by this, which is some flow field. And now they want us to calculate the circulation around a circle who has a center at 0 by 0 and has a radius of unity. So since it is a circle that they are asking us, and we know that circulation is given by nothing but line integral of v dot ds. So we have to take the dot product. We have to take a small section ds of this particular circle ds, and then dot product it with the velocity along this small strip, and then integrate it for the entire circle, entire circumference of the circle. So let's try to do that. And since we are talking about circles, it'll be much easier to deal with polar coordinates r theta than the xy coordinates. So I'm going to change my psi in terms of polar coordinates. So psi is equal to half ln of root x square plus y square. And we know that from our unit conversions, x is equal to r cos theta and y is equal to r sine theta. So I'm going to use this over here. So ln of root r square cos square theta plus again inside the root r square sine square theta. All right. And now I'm going to take r square common from that. So psi is equal to half of ln root of r square into cos square theta plus sine square theta. Sine square theta. So half ln of, so cos square theta plus sine square theta is 1. So this becomes root of r, and so nothing but r. So psi I have converted in terms of r, in terms of r theta coordinate system. Now the next step is to find the velocity, because to find the circulation I need velocity, right? V dot ds integral. So psi is my velocity Vr is given by minus dou psi by positive dou psi by dou theta by r, and my v theta is given by dou psi by dou r minus dou psi by dou r plus dou psi by dou r. It's all right. So calculating Vr is dou psi by dou theta, and since psi is not a function of theta, this is basically 0. And V theta, if I write it, is minus dou psi by dou r. So differentiating this expression with respect to r, I get minus 1 by 2 integral of differential of ln r is nothing but r. So my V theta is minus 1 by 2r. So V theta is 1 minus 1 by 2r, and my Vr equal to 0. So my velocity at every location is going to be just V theta alone. So velocity, I can write it as Vr in r coordinate and V theta in theta direction. So just writing in terms of a velocity vector. So this is 0 plus minus 1 by 2r theta cap. Theta cap is nothing but a unit vector in the theta direction. Now finding the circulation value over here. So circulation is nothing but line integral of v dot ds, and ds is again a vector. So let's look at how can we find the ds vector over here. So if I take my circle and I take a small strip ds over here. That's an infinitesimal strip, and which is covering my sector d theta. So d theta ds, and I have the radius r over here. All right. So from my typical geometric analysis, I know that my ds is nothing else but r d theta, right? Since d theta is an infinitesimal angle and ds is an infinitesimal strip. And then the direction of ds is nothing but theta cap. So this strip, basically the line vector basically points in the theta direction, right? The tangential direction basically. So my gamma here is going to be nothing but line integral of v, that is nothing but minus 2r theta cap, dot producted it with r d theta cap. So since both are in the theta cap direction and it's a dot product, so I can write my gamma as line integral of -1 by 2r into r d theta. All right. And then the limits of the integral would be nothing but to cover my entire circumference of the circle, I need to start from theta equal to 0 and then come back at theta equal to 2 pi. So my limits of the integral will be 0 to 2 pi. So gamma will be nothing but integral 0 to 2 pi. And from the previous case, from this previous expression, r and r can be cancelled. I'll get -1 by 2 d theta. An integral of d theta is nothing but theta in itself, and applied over the limits 0 to 2 pi. And I'm sorry, I forgot a negative sign. So gamma is nothing but negative of this integral. So let me add that negative sign everywhere. Negative, negative, and negative. So negative plus negative will be negative, and negative will give you positive. So this will be nothing but 2 pi minus 0 by 2. So gamma will be equal to pi. So your circulation around a unit circle comprising the origin is basically option B, gamma equal to 1. Okay, so these are all the questions, and I hope you guys would have understood the concept behind in solving them.